What's happened now? Oh, sorry, I glitched there, but I hope that I have now ended the screen share well. I will be handing over to Matthew Bales, who will be introducing you to Pulsars proper. Matthew, can I hand you the screen share?
Thank you, Marissa. You should be seeing something saying the joy of pulsars with Meerkat.
We are.
Great. Okay, well, it's a pleasure to be able to give this talk. I'm from Swinburne University of Technology, which is a university in Melbourne, Australia. We're currently under lockdown, but it's nice to be able to escape into the virtual world to be able to talk to all of you today about one of my favourite things, which is our radio pulsars. So Meerkat is one of the greatest telescopes in which to discover and examine pulsars with, and I'm going to show you some of the highlights, but also teach you how pulsars work. And to understand a little bit of why we want to do that, we're going to go back in time. And I know a lot of you have different backgrounds and levels of physics training. So we're going to start off with what I call gravity's geniuses. So starting at Galileo, Kepler, Newton, and then Einstein. And by the end of my talk, you'll see how Meerkat is helping us to explore Einstein's laws of physics. So our understanding of gravity changed a lot from ancient times until now. It started off with Galileo, who was the first person to point a telescope at the stars. And he knew that Jupiter was a star in the sky that traveled around the constellations. And when he first placed his telescope on it, he was shocked to see that Jupiter actually had some companion moons. And he thought, well, if Jupiter has moons and the Earth has moons, maybe Jupiter and the Earth are a little bit the same, but the sun is different. And so this displaced the place of the Earth in the universe from the center to one of many planets orbiting the sun. Kepler was the first to apply rigorous mathematics to the trajectories of the planets around the sun. And he deduced that there were mathematical relations between how the planets moved and where they were in the sky. So he deduced that the planets moved around the sun with the sun at one focus of an ellipse. The speed of the planet depended on how far away it was from the sun at any given time. The closer it was, the faster it moved in an inverse relationship, or the law of equal areas. And amazingly, he also deduced that the amount of time it took the planet to orbit the sun depended on the semi-major axis to the 3/2 power. And he saw this as the hand of God in everything. Newton came along, and during another pandemic, he was sent home from Cambridge, and he came back with the laws of, or Newton's laws of gravity and integral and differential calculus. It's not a bad effort for a pandemic. It's achieved a lot more than I did in the last 18 months lockdown here in Melbourne. But he showed that Kepler's laws were just a natural consequence of his own universal law of gravitation and the fact that force equals mass times acceleration. And then Einstein came along and realized that if the laws of gravity were anything like the laws of electromagnetism, any two bodies orbiting each other should give off a gravitational wave analog of light. So here I've got two black holes orbiting each other. If you ever could get two black holes very close to each other, they should give off gravitational waves so rapidly and with so much energy that it would suck energy out of the orbit, and the two black holes would enter a death spiral and give off a burst of gravitational radiation. But Einstein realized that the stars he knew about in his time were not sufficiently dense for gravitational waves to be of any consequence. Here you'll see a picture of the Earth, and we've got Africa just passing, which is very timely. The Earth is 40,000 kilometers in circumference, and this is how the meter was originally defined. There were going to be 10 million meters from the North Pole to the equator. And the Earth, of which we're very familiar, is not actually that big by galactic standards. So if you actually look at Jupiter and compare it to the Earth, which is what I can do here, you'll see that Jupiter is this big fluffy planet. It's only about a third of the density of the Earth, and you could actually fit about 100 Earths inside Jupiter. If you actually look at Jupiter compared to the Sun, you realize that Earth is now some pathetic little dot here. And you can fit 1 million Earths inside the Sun, although the Earth is more dense than the average density of the Sun. And at the core of the Sun, the temperature is extremely hot. It's over 1 million degrees Kelvin. And it's basically a big nuclear reactor. And it's forcing hydrogen atoms to fuse together to form helium. And this is the great nuclear power source, which is powering the Sun. The Sun is not actually a very large star by galactic standards. And if we look at a blue supergiant, this is a star that's 10 times the mass of the Sun. It lives only a very short time compared to the Sun. The Sun will live for about 10 billion years. A normal 10 solar mass star, on the other hand, only lives for about 10 million years, so about a factor of 1,000 less than the Sun. And at its core, it's causing not only hydrogen to be converted to helium, but helium to carbon, all the way up until you get to iron atoms. And so at the cores of these stars, after about 10 million years, you get a massive iron core. And the poor old electrons and protons at the cores of these stars can't withstand each other's normal electrostatic repulsions, and you end up fusing the electrons and protons into neutrons. And the cores of these stars, which is only about the size of the Earth, but it has a mass of something like 500,000 Earth masses, collapses, and you end up with what's called a neutron star. And here is an animator's impression of a neutron star. They really do spin this quickly, which is incredible. So this one here has a spin period of about a second, and it has a very intense magnetic field. And this neutron star has an incredible voltage across its polar cap. If you spin a magnet that doesn't like it, it causes electrons to be ripped off the surface of the neutron star. And these are radiated along what we call open field lines, and you get this lighthouse beam of emission sweeping through the universe. And if we're fortunate enough to have that hit our radio telescope, we end up with a pulse of emission once per rotation period. So although this neutron star is spinning very rapidly, it's only about 20 kilometers in diameter. So you've got something about the size of Cape Town spinning once every second. But neutron stars actually can spin even faster than that. And if we look at the one of the faster millisecond pulsars, this is one that Marissa showed us before. It's got the romantic name of 0437 minus 4715. You can see that every 5.757 milliseconds, we're getting a pulse of radiation hitting the Meerkat Telescope. So this is the radio frequency on the y-axis, and we've got time on the x-axis. And you can see these pulses first strike at the top end of the radio band, and then they sweep down. And this delay is caused because when the radio waves travel through our galaxy, every time they come across an electron, they are delayed by a very small amount of time. And this builds up in a kind of quasi-quadratic fashion. It's actually 1 upon the frequency squared is when the pulse arrives at our telescope. And so we can work out how many electrons there are between us and the pulsar by looking at the curvature of these pulses. If we fold this data at a period of every 5.757 milliseconds, we end up with a mean pulse profile, which is very stable. So if you look down on our galaxy, the sun is right here in the middle of all these pulsars, and we have what's called a selection effect, where the pulsars appear to be clustered around the sun because it's so much easier to find something near you than far away. So each of these dots is a known pulsar. Every one with a green circle is what's called an eccentric pulsar. It's a pulsar going around with an eccentric orbit around another star. And the red dots represent the binary pulsars. These are pulsars going around other stars in circular orbits. So if we look at the magnetic field spin period diagram, this helps us think about the pulsars and how they come about. So young pulsars are born spinning very quickly, roughly between 100 and maybe 10 times a second. So they're born over here with high magnetic field strengths of about 10 to the 12 Gauss. To put that into context, a fridge magnet is about 100 Gauss. So these are about 10 to the 10 times stronger than a fridge magnet. If you spin a fridge magnet at 50 times a second, it hates it, and it gives off a lot of energy, and the pulsar moves across this diagram to what we call the pulsar island. These are kind of where the boring pulsars live. They only spin about once a second, and then eventually the pulsars die after about 10 to 100 million years. The higher the magnetic field, the more rapidly you move across this diagram, and the quicker you die. But then we've got this curious little trail of pulsars heading down here to what we call the MSPs, or the millisecond pulsars. So the fastest of these spins once every 1.38 milliseconds, but they only have these magnetic field strengths of about 10 to the 8 Gauss. And they slow down their magnetic field's so weak that they actually live for about 10 billion years. And we call these the resurrected pulsars. So the pulsar is born, dies, and then it somehow ends up here, and we're going to see how that occurs. So I've got a little computer game here, which basically has two stars in it, and I can control it. So stars are often born in pairs, so most massive stars have a companion. And what happens is one of the stars ends its life, becomes a red giant, and it actually transfers material to the other star. And so you get this kind of role reversal where you get the originally biggest star, it becomes a bit smaller because it's transferred matter when it becomes a giant after swelling up. And then it blows up. And when it blows up, we end up with a neutron star, and it's often in an elliptical orbit. So I can put on the little trail here showing that elliptical orbit. So this is just obeying Kepler's laws, where stars going around another star travel in elliptical paths. And the neutron star in this case is spinning at about once a second. They don't really go around the other stars every 10 seconds. It's more like a year or something, but I've just sped it up for you to be able to see that. And I can turn this thing a little bit more face on, and you'll see the nice elliptical orbit and the pulsar beam. And so if we get lucky and this thing points at the Earth, we can actually map the orbit by counting the time between pulses. So this is how pulsar timing works. You just work out when the pulse hit your telescope, and then you can map the orbit, but you can only map it in the radial direction. You can't map it sort of east-west, if you like, in this diagram. So eventually, after 10 million years or so, the pulsar dies, and the companion starts swelling up, and it becomes a red giant. And the material at the surface of the red giant would rather fall onto the neutron star than stay bound to this star once it reaches a certain critical dimension. There's something called the Roche lobe. It's an equipotential surface. And then when the material exceeds what we call the Roche lobe, the material on the outside wants to fall towards the neutron star. And so it falls, the neutron star gets out of the way, and you end up with this disk of material. This is called an accretion disk. And the material rubs against each other, and this gives off energy, and it spirals down towards the neutron star. So we can put this system, you can fly around here and view it from edge on, and you get these very thin accretion disks of material, which are very bright, and they actually give off X-rays. If you grab an X-ray telescope and look out into the disk of our galaxy, you see a whole lot of these systems living in our galaxy. And when they go behind their companions, you get an X-ray eclipse. And then when they come back into view, you see the X-rays again. And you can work out roughly the masses of the stars and the neutron stars. And these were how some of the first neutron stars were discovered. Now, there's a beautiful thing happening here, which is that the material near the neutron star is spinning so rapidly, it actually makes the neutron star rotate more quickly. And so this is how the neutron stars go from that dead part of the diagram, where they were very slow, only spinning once every 20 seconds or so, to the very rapidly spinning section of the diagram. And they can spin it up to about 1,000 hertz, or in about 1 millisecond. This accretion of material seems to destroy the magnetic field as well. So you end up with these low magnetic field neutron stars that basically spin forever. So eventually this star stops its swelling. If it's not very heavy, it becomes what's called a white dwarf, which is a really, really boring star that's just sits there doing nothing. However, if this star is big enough, it too will blow up, and you'll end up with another neutron star. And that's quite an exciting option. So once the material stops being transferred to the other companion, we've got a circular orbit. This star, if it blows up, leaves behind another neutron star. And I can put on the little trails here. And you'll see that these two stars are also obeying Kepler's laws. So let's fly in, shall we? And have a closer look at this system. So you end up with these beautiful eccentric orbits, but the speed of these neutron stars around each other can approach about 1% of the speed of light. So they actually obey Einstein's laws, which dictate that the angle between the two stars rotates around in a kind of rosette fashion, and you end up with what's called an advance of periastron. And so the neutron star is actually being attracted to not where the other star is, they're being attracted to where it used to be. And that gives rise to this precession of the orbit. So let's have a look at some of that in a more graphical form. So we understand how these systems work by creating what we call a standard pulsar profile. This is just an integrated pulse profile, the average pulse profile. And every time we observe, we get another pulse profile, and we cross-correlate these, and we end up with things called arrival time. So when did the pulse hit our telescope? We subtract where the Earth is around the solar system, and we end up with a map of any orbit of the neutron star going around the other star. So this is just saying the observation is some shifted version of the standard profile times a constant plus radiometer noise, because there's electrons in our telescope rattling around which give off this horrible scruffy stuff down the bottom. So one of the most famous neutron stars is called 1913 plus 16. It was discovered by Russell Hulse, who was a PhD student, and Joe Taylor. And they used the sadly now defunct Arecibo telescope to discover this neutron star. And they realized it was in this very eccentric orbit. And this is a result of the eccentricity of the orbit. If it was a circular orbit, it would look like a sinusoid. So the neutron star spends a lot of time a long way from the other star, and then has its close encounter, and then goes back. And this is just Kepler's laws. So it's moving very rapidly and is very close to the other companion here. Anyway, these guys discovered two neutron stars going around each other every 7.75 hours and traveling at something like 400 kilometers per second near this position here. This meant that the two neutron stars were close enough that they were giving off gravitational radiation. This is the gravitational analog of light in electromagnetism. When an electron and a proton whiz by each other, they give off a photon. Two neutron stars going around each other give off gravitational waves. And this causes the orbit to shrink. In this case, it shrinks by 3.1 millimeters every orbit, or about a centimeter per day. And if you're very patient, which Joe Taylor was, he actually used this to verify the fact that gravitational waves existed, and it gave the impetus to build things like the LIGO gravitational wave detectors. So because of the binary pulsar, we knew that gravitational waves existed. Scientists went to the government of America and said, we'd like to build something to detect gravitational waves. And on the 17th of August, 2017, they were monitoring the nearest million galaxies for gravitational waves. And indeed, two neutron stars merged, and we can fly in to the galaxy that of relevance. It was this little green dot here, and there was a neutron star merger creating a new type of explosion called a kilonova. This is an elliptical galaxy. So way out here in the halo, these two neutron stars merged, and there was a brand new star which lasted for about a week. And virtually every telescope on the planet was looking at this thing. So what did they actually see? They actually saw two neutron stars merging. And this was because our pulsar observations had shown that gravitational waves existed way back in the 1980s. This system will actually take 300 million years to merge, but you can work out how often that occurs in our galaxy. Go out to your government, get $500 million, build gravitational wave detectors, and win yourself the Nobel Prize. So this is the frequency of the gravitational wave on the y-axis versus time. And we actually got to see the last 4,000 orbits of this system over about a 2-minute period. And then about a second and a half after they merged, the gamma rays escaped, and we got a burst of gamma rays hitting the Earth. So this is actually how elements like platinum and gold are made in the universe. We merge neutron stars, create a ridiculous pool of neutron stars, and you can create the elements higher than iron. So this was the dawn of multi-messenger astronomy. So this is the telescope I'm most used to using. This is the Parkes radio telescope. And until Meerkat was built, this telescope had a monopoly on neutron stars in the deep south of our skies. This telescope is 64 meters across, and Meerkat is 64 dishes, each of which are about 14 meters across, and put together have about 3 times the collecting area of Parkes. They also can move around the sky a lot faster than the Parkes telescope can. And they have very cold receivers, which means that we can do our pulsar science more rapidly with the Meerkat telescope. Having said that, this telescope has found over half of all pulsars known. So I'm now going to talk about the Meerkat telescope. Marissa's already given you a nice introduction. There's a pulsar timing project of which I'm the leader called MEERTime. You can go to meertime.org to learn more about it, but it has 4 key projects. A pulsar timing array. This is trying to use gravitational waves from supermassive black holes in the distant universe, or their effect on millisecond pulsar timing to detect them. There's relativistic binaries, which are looking at things like 1913 plus 16, the 2 neutron stars orbiting each other. There's swarms of pulsars and globular clusters, which Meerkat is good at discovering and timing. And because of the agility of this telescope, we can actually monitor 1,000 pulsars. And so there's a project called the 1,000 Pulsar Array. So millisecond pulsars can have their periods determined to ridiculous accuracy. So this is the spin period of 1909 plus 3744. It's got this very needle-like pulse profile. It's only about 40 microseconds wide. And by timing this for many years, we've been able to determine that the spin period is 2.947108069160717 milliseconds, which is quite incredible. It has a white dwarf companion, and because the neutron star is going around the white dwarf, we can map the orbit very accurately. So to give you a refresher of what this would look like, in this system, we have about a 1.4 solar mass neutron star. It goes around in a little orbit, and then there's a much bigger orbit being traced out by its white dwarf companion, which is about 0.2 solar masses. It's got a very, very circular orbit. We're going to see just how circular. So every time the pulse goes past us, here on Earth, we get a pulse. I'll try and rig that up. Oh. So we get a flash of radiation, and we can work out the projected semi-major axis of this system. So the radial distance to the neutron star, and map the orbit. And that's exactly what Ryan Shannon's been doing. He'll give you a talk later on. And so the orbit in this case has an orbital eccentricity of I think it's 60114. The diameter of the orbit is 569,000 kilometers, and the difference between the semi-major axis and the semi-minor axis is only 3.7 microns. So 3.7 millionth of a meter, which is quite incredible. The other thing that happens in this system is as the light travels past the white dwarf companion, you get something called a Shapiro delay. There's more space-time compressed around planets and stars and white dwarfs. And we can actually see the extra delay that the light takes to reach us by plotting when it arrives as a function of the orbital phase. And you can see there's about an extra 15 or so microsecond delay when the light travels past the white dwarf than there would be if it was a purely circular orbit. So we can use the shape of this delay and the amplitude to measure the mass of the companion and the orbital inclination of the system. If you subtract off all those effects, you get amazing timing accuracy in the system. If you integrate for an hour with Meerkat, you can work out the arrival time to 11 nanoseconds. We do much shorter integrations, and so the RMS residuals, this is the timing model, or the data minus the timing model here is only of order 83 nanoseconds, so less than 0.1 microseconds. Meerkat has such amazing sensitivity that we can actually see individual pulses, and this pulsar actually turns off and leaves behind, it goes into a bit of a low state, and Matthew Miles, who's probably on the call, has been doing this for his PhD and just submitted a paper on it. If you look at the brightest pulses from this neutron star, you can see that they jitter around a little bit, and this is what limits our timing precision. There's enough signal to noise to do better timing than the 11 nanoseconds, but the neutron stars are slightly imperfect clocks, and this little jitter just is enough to frustrate our efforts to easily measure things like the presence of supermassive black hole binaries in the universe. There's a pulsar that you can only see from Parkes and Meerkat, 2241 minus 52. This means it's 52 degrees south of the equator. And we set a new world record for precision timing. If you integrate all this data up in 1 hour, you can time this pulsar to an accuracy of just 4 nanoseconds. This is the amount of distance that light travels in about a meter, or 1.3 meters. we found that the different pulsars have very different amounts of what we call pulse jitter. And this one here, timed by Aditya, who's going to be one of your lecturers later, was the world record holder. I think he's now got it down to 3 nanoseconds, but some of them are not very good clocks, others are exceptionally good. This is the most relativistic pulsar we observe with Meerkat. It's called the double pulsar. It's 2 neutron stars going around each other. And once again, you can see this extra delay that is caused as a function of orbital phase due to the fact that the neutron star emission has to travel past another neutron star. What we've got on the right-hand side here is how the orbit is shrinking due to emission of gravitational waves. And it's now getting here about 20 minutes faster or earlier than it should have. How am I doing for time, Chairperson?
Just under 10 minutes, Matthew.
Good. This double pulsar is extremely interesting because as one of the neutron stars goes behind the other one, it actually gets eclipsed. Because the light is traveling through the magnetosphere of the other pulsar. So one of them only rotates every 2.7 seconds. The other one rotates every 20 milliseconds. And this is the average profile here as a function of time going up on the y-axis. And you can see we've got steady emission, and then it goes into this stoppy-starty. I call these the tiger stripes, or the Tasmanian tiger stripes. And you can see that the neutron star emission is modulated, and the modulation period is actually the spin period of the B pulsar. And Marcus Lower, who's one of our PhD students at Swinburne, is doing this for part of his PhD. Here we've got what the Meerkat data looks like compared to the previous best data in the world, which is with the Green Bank telescope. And you can see that our signal to noise is far superior. Unfortunately, this means it's a lot harder to get all the subtle effects correct because we've got so much signal to noise that we're struggling to model this as easily as it is to model bad data. But nevertheless, we're making good progress on that. So this is the double pulsar system. The 2 neutron stars go around each other. The orbital eccentricity is only about 0.1, but they go around each other every 2.4 hours. And so we're in this very fortunate position that this neutron star was discovered, and the orbital inclination angle is about 89 degrees. Whoa, it's getting a bit bright. It's migraine inducing. I'm going to travel back up because it's hurting my head. But because of this, when the neutron when the photons from one neutron star pass near the other star, they get modulated by the spin period of that other star. I'm going to move or change gears now, and this is a solitary pulsar. This one was discovered in the Large Magellanic Cloud. That's a nearby galaxy. So this is an extragalactic pulsar. It's actually about 50 kiloparsecs away, whereas your average pulsar in our galaxy is only a few kiloparsecs away. This neutron star rotates about every 50 milliseconds. So you've got the neutron star spinning every 20 milliseconds, but it has a very high magnetic field strength. And neutron stars like that occasionally give off very large radio pulses. We call them giant pulses. And these are a little bit like these fast radio bursts, which are bursts of emission that come from other galaxies. And we're not 100% sure what causes them, but they have certain characteristics which are very similar to what Marissa Haya observed in this system in a recent publication. So Marissa was our first speaker, and she wrote a paper showing that some of these giant pulses, there's just a single rotation here, only have these very limited band transmissions, and this was the first time that had been seen. If you look carefully at these pulses, this is just a single pulse from this neutron star. and it has a high degree of linear polarization in it. And so sometimes the individual pulses can be very broadband, but at other times you have these little narrow ones. And this is similar to what we see from some fast radio bursts, where some of them are very broadband, others are much more focused in their radio emission. And Marissa was the first to show that a neutron star relatively nearby to our galaxy could do the same sort of emission patterns that we get from some fast radio bursts. So here's a zoom in, and you can see that the pulse is virtually invisible across much of the radio spectrum, but it does light up between about 1400 and 1500 megahertz here. And this is just a reminder that the voltage across the polar cap really depends on how fast it's spinning and also the magnetic field strength. So I'm just going to finish up by talking about globular clusters. These are ancient swarms of about 1 million stars. They all orbit a common center of mass. And at the cores of these systems, you can actually get collisions between giant stars and neutron stars. And this capture of neutron stars by the giants can lead to mass transfer, recycling of the neutron star to millisecond periods. And so if you actually look at one of these globular clusters with a radio telescope, it looks as though the light would be blocked, but that's just due to the finite atmospheric effects that are at play here. The radio waves can escape quite unimpeded. And when you point Meerkat at one of these neutron stars, you see whole lots of different pulsars. They've got different pulse shapes, which are kind of unusual, from the very narrow to these ones that seem to be on virtually all the time, ones with nice double structures. And Meerkat's been very good at finding neutron stars in these clusters. If you plot where they are in the cluster, they focused on the center. And they do these cool things where the neutron star is happily pulsing away and then it disappears and then it comes back again. And you can see as it's coming back, if you squint, you can actually see there's a little trail. And this is because there's a blob of material that's been blocking the neutron star and it's causing extra dispersion. And so you get a delay in when the radio pulses are hitting us. So this is the pulse phase on the x-axis, and in time you can see that there's this eclipse, and then as it comes out of eclipse, the radio waves are initially going past a whole lot of electrons and then less. One of our Italian colleagues, Rodolfi, I think it is, discovered an eccentric binary in one of these clusters, NGC 6624G, and he's using the fact that it's eccentric to measure its advance of periastron and infer masses. In this system here, the orbital period is only 1.5 days, but the orbital eccentricity is 0.38. Some of these neutron stars don't just have a simple eclipse, they have what we call a black widow scenario where the neutron star is devouring the companion. And when it's doing that, you get these episodiotic emission patches where there's clouds of material stopping the neutron star's transmission from occurring at all. Others just gently fade out. So in such a system, the what's left of the companion star is rather pathetic, often only about 2% of the mass of the sun. And the neutron star's orbit is very, very tiny. And we can actually put on the orbit and fly in, and you'll see that I'm hoping you'll see, where is it? Well, maybe the orbit is trapped in the well, that demonstration didn't work too well. Like I'm going to quit while I'm ahead, fly back out. Oh, actually, I know what I have to do. There we go. So these are in a circular orbit, but the neutron star is about 70 times heavier than the white dwarf. So its orbit is very tiny. And there's material being lost in the system, and it's causing the neutron star emission to cease altogether. So we can use observations of the pulsar. You can see his little orbit here just in there to understand how the mass is being transferred and lost in these systems. And then finally, we're going back to our old friend 0437. This was the pulsar I showed right at the start of the talk with its 5.75 millisecond period. It's got this incredibly complicated magnetic field structure and pulse profile. You can map the position angle of the magnetic field to learn about its geometry. But this system is so bright that Daniel Reardon, who's one of our chief organizers of this conference, realized that the power being received from the pulsar as a function of both time and radio frequency has this beautiful mottled effect. And if you do a two-dimensional Fourier transform, which breaks this down into the characteristic frequencies, both in time and frequency, you get these beautiful parabolic arcs. And Daniel monopolized Meerkat for a week and showed that the curvature of these arcs changes over the course of the week. And he's using that to map where the scattering of the radio emission is occurring between us and the pulsar. And he found a very low curvature arc in this 2D FFT of this diagram here. And this is actually caused by this bow shock. As the neutron star is traveling through the interstellar medium, it's lighting up the interstellar medium with its energy and causing a bow shock, the same way a ship going through the ocean has a bow shock in front of it. And the radio waves are being scattered as they leave the bow shock. And that's causing this very low frequency arc to appear. And he's been able to determine the geometry of the system based on the arc parameters. So I hope that's given you a little bit of a taste of the Meerkat Telescope. It really is an amazing telescope. There's lots of potential projects, both in globular clusters, testing relativity, searching for supermassive black holes, which I didn't go a lot into, but basically by observing a lot of the so-called millisecond pulses, you can use them as a massive gravitational wave detector, and also learning about pulsar emission physics. And so if you're interested in doing projects with us at Meertime, this is the website, but I might just stop sharing there and ask if there's any questions from the chat, or we'll go on to our next speaker, whatever Marissa deems appropriate.
Thank you so very much, Matthew. That was a great talk. And yeah, thanks for showing us all the exciting and type of science that you can do with Meerkat and with pulsars. There are a couple of questions. I'll read them out to you from the Slack channel. I'm on the Lecture 2 Slack channel for other participants if you want to follow along. Also feel free to add to those question sessions. So what's the first one here? Aniket wants to know, Matthew, whether this is coming from your talk on how MSP evolution works. Does every millisecond pulsar show X-ray accretion?
So very few of the millisecond pulsars are still accreting. So we only know of, I think it's at least one, but maybe it's a few by now, what they call transitional millisecond pulsars, where sometimes they're an X-ray source and sometimes they're a radio pulsar. But probably the first 50 examples of millisecond pulsars had no evidence of an accretion disk anywhere in the system. Although millisecond pulsars, if you look at them for long enough with an X-ray telescope, you do usually see an X-ray profile, but that's very different X-rays. That's from the magnetosphere, that's not from the accretion disk. So I think there's only one or at most a few examples where we have neutron stars that are both X-ray sources and radio pulsars. The X-ray material seems to be very opaque to radio waves, so it's only when they transition between an X-ray source and not we see the radio pulses.
Thank you. And there was also a question from James, who's asking if there are any space-based planned projects to search for the pulsars that we can't see from Earth.
Yeah, so the geometry of our galaxy is such that even if we traveled at the fastest the rocket's ever gone for 10 years, we would still not really see any pulsars that we don't already see. So the pulsars are just ridiculously far away. And if you traveled at a kilometer per second for 1,000,000 years, you'd only travel a parsec. And the closest pulsar is 156 parsecs away. So there aren't any real projects to put radio telescopes into space. Although you could do some interesting parallax studies by having a telescope, out past Jupiter or something.
And then just a recent question coming in from Buntu asking what causes the material to move from the red giant star onto the neutron star?
Yeah, so once you run out of fuel in the core of a star, the interior of the star actually starts to collapse because there isn't the radiation pressure to hold it up anymore. And that liberates a whole lot of gravitational binding energy, and that heats the outside of the star with radiation and causes it to swell up.
And then I think the second part is, and then what causes the material to move to the neutron star?
Yeah, so as the star gets larger and larger, the gravitational force of the neutron star is a 1/r² rule. And it turns out that if you compute the force that the material is experiencing, as it gets closer and closer to the neutron star, you get to a critical point where it would rather fall to the neutron star than stay bound to its companion.
Thank you.
So it's just
questions.
Okay, please go ahead.
Yeah, there are many more questions coming in. Let's see if we can get through a couple more. Preeti is asking why we see the radiations from pulsars not as continuous, but as these sort of series of small packets, probably in reference to your animation.
Yeah, so you can think of the neutron star as a massive particle accelerator, and it's giving rise to relativistic electrons. The electrons are charged, so when they see a magnetic field, they like to travel along the field lines, but not perpendicular to it. And because the magnetic field is spinning, we get collimated emission. And so it's only once per rotation period that we are in the right place to see like the lighthouse beam of this collimated emission being channeled by the magnetic field lines.
Thanks. And then also on the Zoom chat, there was a question asking, how can we differentiate between radio pulsars and X-ray pulsars?
Yeah, so the definition of a radio pulsar is one that pulses in the radio. So you point at it with a radio telescope, and if it's you're seeing pulsations, you call it a radio pulsar. Often we don't independently find these things. We have a hint that there's one there with a radio telescope, and then we point an X-ray telescope or vice versa. But it really just comes down to, is it giving off enough photons for my radio telescope to be able to see the pulses?
And then one from Sarvesh Garat asking, do we take dispersion after plotting the dynamic spectrum to take care of those delays due to the ISM? And a second part question, also the signals we consider is above how much sigma so that there won't be too much noise.
If Daniel Reardon is online, I might throw this one to him because he is the world expert on these dynamic spectra. Daniel, are you with us?
I am. I'm sorry, I was replying to Marissa. Could you repeat the question?
All right.
The question is, when do we take care of the dispersion? Is it after plotting the dynamic spectrum or before?
All right, so the dynamic spectrum is a plot of the pulsar's flux as a function of frequency and time. And the way we calculate that is by having a template model of the pulse profile and computing the signal to noise of that profile. And that's best done after de-dispersion, because you align all the pulses and sum them up in time after that process.
Thanks. And then the second part to that question was, what do we consider a signal? So above how much sigma so that there won't be too much noise?
It's a very good question. So obviously the significance of the signal increases the brighter it is. So generally we like to see our pulsars have at least 5 sigma in order to keep their times of arrival.
Yeah, and of course, students will also learn the more accurate you want to time your pulsar with, the higher your requirement on signal to noise. We've got, I think we should keep this question session open for a little while longer. I can see there's still people typing, and we could probably run this until about 12:30. So let's just wait for people to type out their questions. Of course, if anybody that's already asked a question still wants further clarification from the answer, feel free to just say so, and we can revisit the questions.
Yeah, and asking questions like, no question is too dumb if you don't understand what dispersion measurement, or I use some jargon which I'm so used to, I don't necessarily know what a newcomer is going to get. Don't feel afraid to ask such a question.
Okay, so a question from Sam to you, Matthew, is asking, could you please elaborate more on the GR prediction plot? So let me know if you want to take the screen share. Oh, I get it's free for you to take.
Yeah, I'm happy to do that. So check whether my presentation is still live. Can you see that?
We can.
Yeah, so I'll try and go back in time, if it'll let me. So unfortunately, this isn't PowerPoint, so it's a little bit harder to quickly warp to the relevant slide. Here we go. Oh, I'm pretty happy on that. So this is the GR prediction plot. I hope you're referring to, Sam, because it's called general relativity prediction, so it probably is. So what this is this is assuming that the orbital period, if the orbital period was constant, when would the neutron star get back to the point of closest approach? And if it was constant, all the measurements would just lie along this line here. But what happens is we get this quadratic sort of growth in when the neutron star gets back, because the orbit is shrinking. So you can think of this as the orbit shrinks by, or the path shrinks by about 6 millimeters. No, it's 2 pi r, whatever it is, 2 pi. So it's probably 18, a couple of centimeters after the first orbit. And then when it, because of the gravitational wave emission, but then the next orbit shrinks another 2 millimeters, or another 3 millimeters, which is about 2 centimeters, plus the fact that it's already shrunk 2 millimeters. So it shrinks by 4 centimeters more, and then it's got the original 2 centimeters that's already shrunk the path. So you get this quadratic growth. So it sort of goes 2, then 6, then 12, then 20 centimeters that it's getting closer. And if you just wait long enough, these things are doing orbits quickly enough that you end up with this quadratic decrease in when the pulse is arriving, and it actually becomes 30 seconds. But this took 25 years, but it was worth a Nobel Prize. So I hope that's a good explanation, Sam.
Thanks, Matthew. There's also on the Xray web YouTube channel, there is a video about the double pulsar if people want to learn more about the details of that system. Matthew, I wanted to mention that there was some interest in the software, the simulation software that you were using. One question that I didn't read out before was asking what exactly the software is.
Yeah, so it's actually there's a computer games piece of software called Unity, and Unity enables you to animate things rather easily. And so if I just share my screen, I can just give you an idea of how it works. Might share, where is it? Here we go. So this is not your sort of standard PowerPoint. If I do F1 here, I think it is. This is actually my talk. So you can see it starts off with an introduction, then it's got some slides, then the geniuses, then bigger than big, and so on. If I do edit actions, this is now my talk. It has this little preview mode. So if I click here on geniuses, there we go. You can see what that's going to be like. And then this is an isolated pulsar. These are just some standard slides. But then the binary evolution is this thing here. And it's actually a bit like a computer game. So it responds to my key presses and so on. If I double click on that, it actually takes me through all of the different stages of the evolution. And I can edit what the spin period is, and whether it's a neutron star plus main sequence, whether the orbital eccentricity, what it is, whether this phase is active or not. And so I can actually create literally an arbitrary binary pulsar, which is kind of a bit overkill, but when you're the director of a national research center, you can commission this sort of thing, which is kind of fun.
Thanks, Matthew. Also a question from the Zoom chat coming out, Sarvesh asking, is there a way to theoretically predict the dispersion value, or do we just do that by varying the value and checking the plots?
Yeah, so we just fiddle with the dispersion in our software until it's removed. But if you actually knew the distance to a pulsar, you could guess it to typically 30% accuracy, just because we have a model of the galaxy's electrons. So if I know something's 150 parsecs away, it's going to have a DM of somewhere between probably 2 and 10 or something like that. Similarly, if I knew it was at the center of the galaxy, it's probably going to have a DM of 1,000.
Yep. And of course, if you know the electron density to the pulsar, you can analytically write out the expected dispersion smear between two frequencies. And so then maybe this will be sort of our wrap-up question to catch all these, quite a lot of questions on near-time projects. So asking how can students contribute to near-time projects, and also and particularly asking if they're moderated projects for which certificates are issued.
So I'm not 100% familiar with the South African system, but we're very keen to get as many students as we can involved in these projects. Normally, we'd like to have a lecturer or something at your host institution who's kind of like a partner, not just working with us one-on-one. But there's also opportunities to do things like apply for PhD positions if you have an honours degree at our host universities if you're prepared to leave Africa or South Africa. But in the first instance, just send us an email. My email is easily discovered saying you're interested. If you're at a university that has an astronomy department, that's a lot easier than if you're at a university that doesn't. But there's also more technical instrumentation type projects that are potentially available as well. So ideally, we would assign you a kind of a mentor, and that would be somebody from within Meertime. There's about 40 of us who are very active. Probably 20 or so of us would be capable of supervising a student. If you want to work on a major project, it's probably an advantage to be in a similar time zone. So a European supervisor is probably preferable. The time difference between Australia and Africa is about 8 or 9 hours, depending on which part of the year you're in. And so it's a little bit more difficult to get that quick responses to things. But certainly we'd be interested in everything from like honours projects, which are probably taking up, a few person months a year of effort, all the way through to masters and PhDs. I don't know what a certificate issue is, but I'm assuming that this is some sort of thing that enables you to get your qualification, and we could explore that.
Thank you so much, Matthew. So I think from my side, probably knowing the systems a bit better, so across the African continent, what Matthew is saying is if you're already affiliated with a university, that makes things quite a bit easier. And so if you are signing up for a master's project or a PhD project at your university, then we can contact Meertime to figure out collaborative projects where you've got a supervisor at your home institute, as well as supervision from the Meertime team. I think that's usually the way in which this works easiest. I think that's more or less it. There's some additional information coming through on the question channel on how we calculate dispersion measure values. So thanks for that, that's really nice. I'll end it here unless any of the other organizers have something they want to add. I think for each session that we add the main information, for each session that we end, the main information we'll give out is just how we start again. So on the program, you would see that there's a lecture starting at 11 on an introduction to programming. If you still have issues with your virtual box, then I wonder if it's not a good suggestion for you to come online earlier. So if we can meet for lecture 3 at 11:45, sorry, I'm saying Cape Town hours now, so 8:45 UT, then that would allow people that are still struggling with their virtual boxes to have some support. Renee, Daniel, do you want to take the mic and add to what I've said?
No, nothing to add. Just yeah. So the UTC time is 9 for the next lecture, which is in 25 minutes for now, from now.
And join earlier if you still have virtual box issues. Cool. All right. Enjoy your break. I hope it involves coffee or tea or whatever you like to do in your break, and we'll see you back here soon. Cheers.
Bye.